Okay. So yesterday, I introduced this idea of kinetic energy and this idea of work. Today, we merge them together. It is what is known as the work energy theorem. So the net work is equal to your change in kinetic energy. All right. Again, we have this concept of energy in science. And so far, we've talked about forces. And I wonder if there's a way to relate how a force acts on an object compared to its energy. And so we've baked up this measure called work that says if you apply a force, a net force on an object over a certain distance, that's going to equal your total work. That's going to equal how much your kinetic energy changes by. Okay. And change in anything is final minus initial. Okay. So final kinetic energy minus initial kinetic energy. But this right here, this is your work energy theorem. Good at that? Okay. So what would make this network positive based upon that? If this value, your final value of kinetic energy, is greater than your initial, that would make this positive. Okay. Just like bring this in with just assuming the mass is not changing. What's going to make kinetic energy greater, finally, is if it's moving faster. Okay, so if it's speeding up, it's a positive network. And if it's slowing down, that gives you a negative network.
This might be a really dumb question. Can you have negative kinetic energy?
That is not a dumb question. That's an excellent question. Can you have negative kinetic energy? So assuming we don't have a negative mass, and your speed is squared. So even if you like forget its speed and put in velocity, it's a pretty user-friendly equation. That's always going to end up positive. So this whole thing's always, kinetic energy will always be positive. Good with that? Okay. So let's dive into applying this. All right, so same numbers as yesterday. Same scenario, but the question is how fast will the box be going after 20 meters if it started from rest? Okay, so full disclosure, you could actually answer this question with what you already have known, with drawing a free body diagram, calculating an acceleration, taking the acceleration and plugging it into a kinematic equation and get the correct answer. Okay, totally legit. I'm going to show you a different way. On the test, I'm not necessarily going to be able to prevent you from doing the old way, but there are certain scenarios where free body diagram and calculating the acceleration with kinetic energy fall apart where work and energy shine. Okay? Specifically, if acceleration is changing, kinematic equations fall apart. Okay? But work and energy are like, I got this. Okay? So on the test, I'm definitely going to recommend going the work and energy route. On your final exam, you have choice. Okay? My guess is many of you will actually go this route sooner than you'll go to what you've learned. But, yep. All right, so what we've got is what we're looking for how fast, so that kind of screams kinetic energy. So we have final kinetic energy minus initial kinetic energy. Okay. And we know that from yesterday that the net work was 2,000 joules. And this is 1/2 mass times speed squared final minus 1/2 mass times speed squared initial. It started from rest. So we know our initial kinetic energy is 0. We go with that? So we have 2,000 is equal to 1/2 times 50 kilograms times final speed squared. So this is 25 divided by 2,000, so you get 80 speed squared. Take the square root of both sides and find that to be 8.9 meters per second. How are we doing with that? We've incorporated the 20 meters already into the work. Like that's where that got used.
So if you just, like if it just asks to find kinetic energy, like, is,
So to find kinetic energy,
because you would take away the initial, so would it just be like, without using the formula, would it just be 2,000?
it will be 2,000. Yep. Good with that? Questions there? So, I'm going to change the scenario. Have a thumbs up when you got something. have a conversation.
So you write the work formula, which is forces per row distance. Yeah, and then so you get forces per row times 15 divided by 1/2 times 100, and then your final speed was 3 squared, and then here your initial speed was 1 squared. That's not true. Does it make a difference?
Okay, correct answer is? Correct answer is A. My hope, okay, so to find the net work, you've got two options. You can go the force times distance route or the change in kinetic energy route. Killer was you didn't have enough, you had the distance, but you didn't have anything about the net force. Okay, so my hope is that you pivoted and you're like, oh, let's try this kinetic energy thing. Okay, so we have the net work is equal to 1/2 mass times speed squared final minus 1/2 mass times speed squared initial. The other thing that I wanted you to see from this is order of operations. You need to square the speeds before you subtract them. So you're not going to say 3 minus 1 and then square it. You're going to square this so you get 450, so 9 times 100 divided by 2, minus 1 times 100 divided by 2, so 450 minus 50 gives you 400. Good? Learn some stuff? Okay. Oh, that was it. No, sorry. Oh, your neighbor, what you think?
That's what I write down. That's not what it is.
Correct answer is? No, you cannot. You can figure out the net force. That's possible. But your net force would be Ftx minus friction times distance. Okay? You can find, this is your net force, but unless I give you friction, you're not going to be able to find tension in the x direction, therefore find tension. Okay with that? So the point of this question is I want you to recognize that this work energy theorem is not the silver bullet for everything. It's like it gives you stuff, some things, but it doesn't give you everything. Okay? Thumbs up or down, I guess. Top your name.
What is It's kinetic force. It's like yeah, I think when you did it yesterday too, and I was being like,
The correct answer is. What do you say?
C.
C. Okay. This would give a net force, that would be negative, therefore negative work. And if you are slower than when you started, this quantity is going to be negative. Good with that? Okay, so you've got two different perspectives, the force perspective and then the energy perspective. Chew on this one for a little bit.
So I think eight. What's the best class? Okay, doesn't have to be actual class. And I feel like I did go. Yeah. I like a GoPro. Track around. Wow, this one.
Have a conversation.
So, while he's driving 60 miles per hour on the course, it sounds like 60 miles per hour, with constant velocity. Yeah, if it's going south of Howard,
Yeah.
something like
Yeah, but if it's going at a constant velocity, then it's 0. But if it's slowed down,
I'm excited. Me too. I'm excited to eat.
first time in a long time.
Really? We had so much cake. But we also like, oh look, look, that was really high. Those are all full size candy bars, so. Wait, did you know that one big top? And you were like,
Alright, Greg, let's take it question by question. So some of the forces in the x direction, are they equal to 0? Does velocity have direction? Does velocity have direction? Fact that so yes, does the fact that we changed directions mean we have acceleration? We have acceleration. Is inertia doing what it wants to do? It's going this way, and then all of a sudden you're like, go that way. Like, what? I want to keep going this way. Okay, inertia is not happy. There is acceleration. The sum of the forces are not equal to 0. So the correct answer for this first part is yes. Okay, sum of the forces are not equal to 0. Okay, now let's talk about work. The net work is, we could look at that, but I'm going to look at this. Does kinetic energy have direction? Kinetic energy does not have direction. It's 1/2 mass times speed squared. No direction. So the fact that I changed directions, the net work, final minus initial, they had the same values of kinetic energy. So there was no change in kinetic energy from the initial point to the final point, so the net work is equal to 0. No. The answer is B. Now, let's unpack that because that's weird. Okay? Here's this question, ready? This question reveals a difference in what we've talked about thus far and now what we're talking about with work and energy. A free body diagram, hang with me. A free body diagram is just a moment in time. Okay? And you found the acceleration and you went, where work and energy, look at a process. Okay? If I started over here and was driving at 60 miles an hour northward and then I hit the brakes, is work done by friction positive or negative? By the brakes. Is it positive or negative work? Negative work. So if I started over there going 60 and here 0, the net work would be 0. Sorry, it would be negative. Okay with that? I turn around and I start speeding back up. And let's say I speed up real fast and I get up to 60 miles an hour here. From the time where I stopped to the point at which I'm now going 60 miles an hour, did the engine do positive or negative work? Positive work. Is everybody okay with that? So if I looked at this, the second half, I've got positive work going on. But if I take the process where I was going 60, going this way, to the point at which I'm going now 60 going this way, the negative work done by the brakes added to the positive work done by the engine ends up being 0. The net work for that entire process is 0. Okay? Kitty?
So how do you know he didn't do any distance?
Great question. I don't necessarily need to know if he did any distance because this is distance rather than displacement. So is that where you're getting at? Like if I ended up here, if I started here and then ended here, are you asking is distance 0?
If the sum of all forces isn't 0 at one point, and it's like the sum of all forces parallel times the distance, how do you know that the distance is 0? Because that would make the net work 0.
Okay. Good question. To answer that, I'm trying to think of a way to do this without using calculus. This is what you're addressing is. It's a great question. So this is. We are adding. Okay, I'm going to try this approach. It's a great question. So we're going to go northward certain distance, okay? And during this process, we've got negative work. Negative work is being done, the slowing down process, okay? And we're going to say that process was negative 200 joules of work. Totally making that up. Okay, so the net force would not be equal to 0 during that process. Okay, and so you'd have a certain value of force of friction times distance to give you that. Right, during the slowing down process. Okay, and then the speeding up process. Let's say it's a different distance. I'm okay with that. And the sum of the forces aren't equal to 0 during this process. And you multiply these two, and then some applied force from the engine times your distance. That's going to give you a positive 200 joules of work. So when you take this whole process plus this whole process gives you a net work of 0. Okay, it's not a moment in time is what you were going at. Like, hey, that's not equal to, it's a whole process. And so you have to add all of that process up.
Okay. So
Okay
that's
with
what
it?
you're saying when it's easiest to use the kinetic energy equation because it can lead you to different answers.
Right. Yep. Okay. All right. Switching gears. So are we seeing the difference between what we've learned so far and how it works a little different? Okay. If you are following along on the PowerPoint, I just jumped back up to lesson 1. All right. Power. Power. This is the rate at which work is done. The rate at which work is done. Or how quickly work is accomplished. is another way to say that. Okay. The equation for power is work, and power is capital P over time. The rate at which work is done. Good with that? The unit for power. What's the unit for work?
Joules.
Joules. Unit for time. Joules per second is equal to a watt. A watt. Watt. Okay. Technically, the symbol, the abbreviation for watt is a capital W. However, that gets kind of confusing with the capital W for work being the variable. So I just write it as watts, just to make that distinction. Okay? And just to make a connection with things that you may or may not have heard of, a horsepower is another unit for power. Just like the King of England at some point in time in history was like, yeah, my foot length should be the standard. And that's a foot. And then we went with it. Okay? Somewhere in history, there was this horse. We'll call him Wilbur. Wilbur, he was I don't know. He's like, that's 1 horsepower. Could do this much work. And the conversion between watts and horsepower, 1 horsepower is equal to 746 watts. Pretty random. But, you know, you don't have to know that. I'm just trying to make connections with stuff you've heard. So, like, you get 2 horses. Like, 2 horses. That's, I mean, yeah. Cool? So. Try this question. a conversation.
So you plug in each and then like see and like say if the work equals this, you could see. Or since it's wrong, and it's like it's wrong. You know what I'm saying? It's like I'm just saying, like. Not a bad idea.
Well, that's why I thought. My hair's always really going. It's gotten better though. Yeah.
Okay, what do you say? Here we go. Okay, force, gravity, applied force, yes? Moving at constant velocity, you know the sum of the forces, R equal to 0. So you have applied force is equal to the force of gravity. Okay with that? And we know the force of gravity is equal to mass times 9.8 rounded to 10. Okay with that? We know power is equal to work over time, and work is equal to force times distance. We're looking for Bubba's, so applied force, which is parallel to the direction of motion, times distance of 2 meters. Applied force is equal to your weight times your distance to get work over your time. So we had 50 kilograms times 10, so 500 newtons, times a distance of 2 meters, so 1,000 joules, divided by a fourth of a second, gives you 4,000 watts. Good with that? Okay. Remember, you got bridges due on Monday.